Today's lecture is Relativistic Gravitation and GR, the General Relativity test. General Relativity was developed by Albert Einstein after he developed special relativity. Why he had to go to introduce totally new relativity? It's not general and special because really they are not connected. It's two different theories. Special relativity still was not able to explain why there is a precession of Mercury's orbit. It's not exactly. It was able to explain a precession. You can get the precession also from special relativity, but the answer is wrong. You get the precession is exactly 1/6, a sixth of the one observed. And such a big mistake, only 1/6 of the real experiment, means that the theory is not describing well what's going on. So the idea was, he thought, we have to build up a different theory for gravitation than for any other forces. And then he looked that in what is unique with the gravitational force, that it acts similarly on all objects, generating the same acceleration. Therefore, the idea was to turn it into geometry. From my point of view, he by occasion falls on the right model, because the only difference, as you will see, is how we extend classical formulas from velocities very far from the speed of light to velocities close to the speed of light. Means all theories assume Newtonian limit. That means when the velocities are small, your acceleration is as in Newtonian dynamics. So the only difference relativity brings in how to take care when the velocity is not negligible. Now this lecture is mainly based on the paper that is written down, from published this year, a few months ago, where I presented most things, but the lecture of today will have new ideas also that grow up from preparing the lecture, and you are the first one to see them. Okay, let's start. You already heard about this in the previous lecture, the basic ideas behind relativistic Newtonian dynamics. So motion of a physical object is influenced by its surrounding force field affecting him. Means that we are in places in our world, there's a lot of fields around, but not all of them are affecting us. And if we want to talk about motion of an object, we have to consider only forces which affect him, its motion. The force field determines the object's own space-time. And inanimate objects move uniformly, that means constant velocity or zero acceleration, in its own space-time. And the reason for this is very simple, because he has no means how to change its velocity. So he cannot change, he must continue to keep its velocity. But in his own space-time, what it means constant velocity, what means a straight line is different. And the influence of gravitational field will be expressed by a metric on the flat space-time. This is different as we had in the previous lecture. In the previous lecture, what we gave him at each point in space, what should be his acceleration, and this was a linear function of the four velocity. Now, his motion will be defined by a metric instead of giving him the acceleration, and the metric will give us the acceleration. And you see the difference will be not linear, it will be quadratic. And therefore, I think eventually, if you want to build up a model that will be able to combine both things, probably bounded symmetric domains or symmetric domains are the one, because that's the only model where I know you have a connection of linear and quadratic maps. And therefore, I think that this is very important. So today we'll talk about when the motion is defined by a metric. What is the formula for a gravitational field? Motion of objects is along a geodesic with respect to a metric. What is the difference in my approach that I'm presenting here and GR? GR works on the curved space-time itself. When you work on a curved space-time, everything becomes very complicated because you have to define everything, parallel transport, you have to define covariant derivative, and you have to have a lot of machinery developed within the theory of Riemannian manifolds, which I will show you is not needed for this, because we work on the flat background. It's the same as I try to explain you the problem to find the shortest route on the globe. You must not do all your calculations on the globe. You can work on the map. And the map is much easier to work. It's a two-dimensional array, and you can use the metric to translate everything to the real space. So we will work on the flat background. Now, what is the flat background for GR? It is as it's observed by far removed observer. The equations of motion are derived by Euler-Lagrange equation, which tells us what are the equations for a geodesic. The metric, how we'll find the metric? In GR, the metric is defined by introducing curvature and a lot of things and trying to implement that the theory has to be general covariant, means invariant under any smooth transformation, which is not physically required, and this takes you very complicated the problem very much, and Einstein's field equation is very hard to solve because it's a nonlinear differential equation, and when you have nonlinearity, it's a lot of problems around it. Each solution is a miracle, and there's not too many solutions known. And also the ones that are known, they have a lot of assumptions around which are not tested. Okay, so we'll use the metric, will be defined. The metric is determined solely on the strength of the source. That's obvious. As the source is stronger, it has to have more influence. The position of the source at the retarded time, because also the gravitational fields propagate with the speed of light, and so we'll use the same presentation of field propagating with the speed of light that we used the last time. But at some point, we'll have to introduce the metric, and this will change. So as the picture from the last time, if the observer is the point P, and that's the world line of the object of the source of the gravitational field, you have to look on the light cone where it was when the field came to me now, what means for me for if I see a star, which is 10,000 light years ago, far from me, so I see what was there 10,000 years ago, but not what is there now. What happens there now is totally not relevant to me. So really what influences me, what is only the retarded position of the object, of the source. And at this point, I'll present the theory which is using Newtonian limit, which is valid for low velocities. Now, in Einstein's theory of relativity, it's valid only for weak fields. We don't need this assumption. our theory is valid for any field strength. You need only low velocity. I mean, that's much more general assumption, and it is with this assumption, without adding any information about any equations, we can define the metric, and when we can define the metric, we will use Euler-Lagrange equations to solve the evolution. I recall Euler-Lagrange equations that we saw in the lecture number 4, I think. And here we use the line interval to measure the distances on real distances from the distances on the map, on the flat background, the x alpha and the x beta measured on the background. And we introduce a Lagrangian, which is the SD sigma, where the sigma is the parameter on our line. You have to be able to measure the distance. Now introduce the C is to make it similar to the known quantities in physics, but you can work without C. And that's what we derived the last time. If you have the distance over the line is the minimal, then you have the equation. The L, the x alpha, is minus the derivative by sigma of the L, the x alpha dot is equal to 0. Those are the Euler-Lagrange equations. And when we calculate this term, the x, the alpha dot, we write that what it is down for this metric. It's C in the numerator, 1/2 of because of the square root, and you have this ds, CDS, the sigma. I use this one, and I differentiate under the integral, get twice because it is alpha and beta are interchangeable, and you have G alpha beta, and differentiate by alpha, you're left with x dot beta. Now, if you look on this, that's like lowering the index beta, making it alpha, but this has differentiation by sigma and divided by the SD sigma, so it is the same as the x, the s, when they take the component alpha. The 2c in the numerator and the denominator got cancelled. That means this term is like the derivative with respect to the arc length. And so if we want to have only one derivative, we need to choose the parameter proportional to the arc length. What will be the other term that we see here? This one, when we differentiate, we'll have one small c, and 1 of the square root will get this term. And when we differentiate by x mu depends on the g, depends on x mu. Those are independent variables to x mu, so that's the derivative. So we get, in order to have only one variable, we introduce proper time as the parameter on the curve, which is the s over c. Why? Because proper time, that's exactly the same as the time of a clock moving with the object. And from now on, the dot will mean always differentiation by proper time. And the equation of motion, this equation which is written here, this part now became, we differentiate by the proper time, and we'll get a c, another one, which will cancel out with this c in the front, and then we'll get another derivative by tau. It is the a mu, that means the second derivative of r by tau, but considered as a covector with the lower index, and it will be the L dx mu that we have here in this expression, 1/2 the derivative of the metric with the x mu, x dot alpha, x dot beta. That's the only thing what we will need from here. We will need also another conservation law. If the L dx alpha is 0, that means that it's independent of one of the coordinates, then the L dx dot, the moment, which is called momentum, is conserved, because this is 0, then the derivative of it is 0, and the derivative is 0, that means it remains the same on the trajectory. That's the main tools which we'll need from this theory: formula for the acceleration and conservation law. Okay, we start to solve the problem for a field outside a spherically symmetric source. That's the main object that we have to consider to check deflection of light, precession of orbit, time delay, and everything else. Because mainly all those objects, those phenomena are related with the gravitational field of the sun. In our solar system, the sun is the major player, is the most massive object. It's spherically symmetric, and its gravitational field is our motions of all our planets have a geodesic motion in this gravitational field. We use bipolar coordinates, as we introduced the last time, in the Minkowski space. The Minkowski space is the flat space of the far removed observer, and with the center at the center of the source. And here's the definition that we had the last time. In the plane xy, we use the regular polar coordinates. Rho1 is the usual r that we used earlier, and Rho0, cos, and sinh are in hyperbolic coordinates in the t and z plane. Now, we can simplify the problem. We can pick up at plane xy by the position of the object, the initial position, and the initial velocity. And this defines a plane. Pi, defined by the initial position, initial velocity. And the whole motion will remain in this plane. Why? Because also the force, which is the center, is in the plane, is acting on P, is also in the plane. So you stay everything in the plane. Therefore, motion in the plane xy will remain there. So we rotate the coordinates and make the plane to be R1, R2 plane. In this case, R3 is 0. That means theta is 0. Now, the retarded position, you remember the retarded position is a null vector. To be a null vector, you must have Rho0 is equals Rho1, we denote it by rho. And you will have here the first row, 0 is rho times cos at 0 is 1. And here you get rho, and this one are with the coordinates with respect to rho and p, the polar coordinate. Now we try to get the metric. So we know the relative position, and we do the following thing. As was also in the previous lecture, we define the direction in bipolar coordinates, taking out r outside. Now, instead of writing rho, I used r because we used everything in the plane xy, where we use the distance parameter r from now on. You take r outside, and you have the vectors now of length 1 in the plane xy, and the time parameters 1. This is y hat is the direction in bipolar coordinates. Direction of influence, direction of the field propagation. Now, what we have said, that that's the only thing which can define as the metric. The metric has to be built up only on this vector. A metric has to have two indices, so it gives you right away how the form of the metric. G alpha beta is the metric of the flat space-time. I put a minus for technical reasons. You can put a, since you have a general function phi, which can depend only on R because of spatial symmetry. It cannot depend on phi, because you can change phi and nothing will change. So it can depend only on R, and it can depend only on one vector, y hat. So this y hat we have to use for it with two indices. You have to lower down the indices. Lower down is without the metric in the space, the flat space. And this way, that's the only way how we can generate a metric based on the fact that it can depend only on one preferred direction in space-time, which is y hat, and that's the form of the metric. It is more convenient to use the basis that we used the last time, which was defined by the local basis and bipolar coordinate differentiation by each one of the parameters. Differentiation by rho 0 gave us d0. Here I'm substituting theta equals 0, so here it became 1, 0, 0. I omitted the force coordinate because it's always 0, so I write everything in 3 dimensions, because the z coordinate is 0 all the time. And then is a vector d1, which is the direction in the r, rho 1, which is now cos and sin theta, and d2 is the perpendicular one. Differentiation by phi gives you this and normalize it. This is an orthonormal basis, and y hat in this basis, it is 1, here you see, and 1 phi is exactly this vector, d1. So, and there's no component for d2. So y hat has two coordinates, 1 and 0. So it's very easy to understand what this is. It has only, if alpha and beta are both 0 or 1, then it's 1, and otherwise it's 0. So what the matrix looks like, here it looks like. The metric eta alpha beta is 1 minus 1 minus 1, because this is an orthonormal basis, and minus phi times, and all the 4 places, where the indices are 0, 0, 0, 1, 1, 1, and 1, 0. So that's very simple form of the metric. That means it is like taking the regular metric and subtracting something of rank 1. This is a rank 1 operator. Now let's see what will be dynamics equation of motion under this metric. So we have to use now Euler-Lagrange equation for motion on this metric. From Euler-Lagrange, that was the formula. I repeated the formula that we had on the previous slide. A mu is a half derivative of g alpha beta x dot alpha x dot beta. In our basis, what is x dot? The first coordinate was connected to CT, and it's CT dot. The second coordinate was R, and the last coordinate was R d phi, and so you differentiate it by tau. Is that the radial velocity with respect to tau? R phi dot is the transverse velocity with respect to tau, and CT dot is the derivative of the time component with respect to tau. Y hat is this 1, 1, 0. So I have to calculate. You see, you'll have here in this metric, you'll have this y hat, and then you'll have to compose them with x, with this one. So I'll have to do the dot product. And I forget to put the y hat here, sorry. I have to correct them. There should be near g alpha beta has to be the y hat, but that you have to differentiate the whole metric. And you have y hat alpha, x dot alpha, etc. So you can take this thing and you take 1 times this and 1 times this, and taking the sum as regular, you take contracting to an index. And then what we'll get, G alpha beta depends only on R. So non-zero acceleration is the one which is related to the first component, A1, and is the following. A1 equals, you take the metric which was written on the above, which is phi here, phi time R, y hat alpha and y beta, that was a part of the metric, and you have to multiply by x dot alpha, x dot beta. You contract y hat with x alpha, you get x t dot plus some dot. The same thing, y beta with x dot beta, the same expression, so you get square. This is the formula for acceleration. You see, it is some kind vector, and here it is the square of the forward velocity, which is contracted to some direction. This is the key formula how to extend acceleration to any velocity. It is extended not in a linear way, in a quadratic way. Depends on the square of the forward velocity. This is the key point when you want to build up the generalized theory. You have to probably start with this formula. To understand it at all, it's not exactly the square of the forward velocity, because it has, first of all, contracting with y, with some kind projecting down on the direction of influence. It's not important for the metric, the forward velocity in any direction. It is only important in the direction where the fields propagate. You project down and take the square of it. Now we have to, the next thing, we have to define what is phi. And if we define phi, we finish the metric. We know the metric, and then we can continue. For this, we'll use the Newtonian limit. We look the formula that we obtained, and we do the following. We take ct dot outside, squared, ct dot squared, you get 1 plus what we'll get here, r dot over c dot. When you divide the r d tau by dt d tau, you get the r dt, which is the velocity in the radial direction, which is vr, the regular velocity, and the c because you divide it by c. Newtonian limit, what does it mean? The acceleration of an object q with zero initial velocity is classical. It means you have to be able to compare this acceleration to the classical one. But you have to be careful. A1 is not the same acceleration. It's not the r dt squared. So how will we compare it? We have to say, since q had zero velocity, so vr is 0. So this term does not exist. 1 plus 0, it's 1. But we have this term, t dot squared. But what is a1? A1 is the second derivative of r by the tau square. But since we lower down the index, and lowering down the index in Minkowski metric is changing the sign to minus, because that's a spatial vector. Now let's write down what it is. D twice differentiated by dt is the same differentiated by tau twice, and twice differentiated d tau dt. The tau dt is 1 over dt d tau. And so you have this additional term here, 1 over t dot squared. So go back here. And so this one is already 1 over t dot squared cancel with this one, minus cancel this one, and you get that the acceleration y is this one, c over 2 phi dot r. That's what's left from this formula. That's the acceleration if we use r and d. What is the classical acceleration? The classical acceleration is the gradient of the potential with a minus, and the potential has only depending on r, so you'll have only in the radial direction, over divided by the mass. Now you have two formulas. Newtonian limit tells you the two accelerations are the same. So you have from here, this must be equal to this. So you get phi dot equals u dot from here, m the denominator, the 2 went up stairs and c went down. So you get such expression. For u dot, you have now from this, you can say that phi equals u plus some constant. But both phi and u must vanish at infinity, so u vanishes at infinity, and phi must vanish at infinity, so there's no constant, and really phi equals 2 over mc squared u. For u, we know that is gm capital M and m the mass of the moving object, so the masses cancel out, so we have 2gm c squared denominator divided by r. That's the formula of the classical formula for gravitation. You can recall it from the lecture number 2. So as there we use for planetary motion, we write this constant that we get here as denoted by Rs. That's what's called Schwarzschild radius. That's a distance that the strength of the field is so strong that in order to escape it, you need to have the speed of light. It means you cannot escape from this radius outside. So you get phi of r is what's called dimensionless potential energy, very simple formula, Rs over r. Rs is a constant defined uniquely by the size of the source only, and r is the distance from the center of the source. So we finished what is the metric. The metric is the G alpha beta is the eta alpha beta, the Minkowski metric, minus Rs over r, which is the dimensionless potential energy, y hat alpha, y hat beta. So we found, without doing an additional equation, using only the symmetry of the problem, using that motion is by geodesic, and equating the two accelerations, the classical one and by the Newtonian limit. This way to present, you'll not be able to do it in GR because they cannot get the Newtonian limit exactly. That's the only way how you can get it exactly. With the T, doing everything, comparing them exactly what the Newtonian limit tells you. Okay, when we have already the metric, now we have to imply the geodesic motion and all the results. So from now on, we are going to use the consequence. We'll start, the first shortcoming that we mentioned was gravitational time dilation. Gravitational time dilation tells you that if you put a clock on a different gravitational level, the rate of the clock changes slightly. In our time, there are atomic clocks with such accuracy that they can measure the difference between two floors in a building. So really, our technology reached to this level of accuracy. Once it was thought almost impossible, but now we are there. Everything is built up on this line element that we obtained. I put together all the metrics with the T brought in. Pr is the one that we found, and it looks like in this form. Okay, gravitational time dilation speaks about a rest clock. Rest clock, that means dr is 0 and dφ is 0. So all those terms fall down, and we have ds square was c d tau square. In this case, it is 1 minus phi c squared dt squared, where d tau is the time increment on the clock positioned at the place r. So c square cancels, and you have dt square is equal to this expression, and you have the formula for gravitational time dilation. It is the clock at the level r is the same at the level t times 1 minus phi r, where phi r is rs of r. That was the famous formula predicted by GR, and it was tested and it works right. So we can go even more. We can get the formula, what will be the time dilation for a clock moving inside the system. So we repeat everything. Take cdt square outside. What will be left? From the first term, we'll get 1 minus phi r. From the second term, what we get? We divide by c square. C1 cancels, and you'll get dr dt, which is the velocity in the radial direction. And over c, that's what's called beta r, the component of the velocity in the radial direction divided by c. When you get into this term, you get dr dt square, which is beta r, and c square. You get beta r square. And this will give you the transverse velocity divided by c square. So you can write it down. Now, here you can combine two terms. This term, 1 times beta r square, and this beta transverse square is exactly the velocity, the two components which are perpendicular, so it's beta square. All rest terms have beta r, phi r. So taking out phi r, and what is left here? 1 from here, 2 beta r, and beta r square from here. So get 1 plus beta r square. Beta r is the r dc dt. This formula tells you dt is 1 over 1 square root 1 minus beta square minus phi r, 1 plus beta r square. Very interesting formula. It tells you it depends. 1 minus beta square is exactly the time dilation from special relativity, the gamma factor. When you have no gravitational field, you get the special relativity. When you have a gravitational field and you have no velocity, so beta and beta, you get the gravitational time dilation. And in general, you get a dilation factor which is also depending on the direction of the velocity. Not only beta square, you have beta r. And beta r, if it changes the sign, 1 plus beta r changes its value. It means the time dilation becomes also dependent on the way you move the clock. Very interesting observations, are different than we are used to seeing. Now we go to the next problem to describe the precession of Mercury. This is the problem related with planetary motion in a stationary spherical symmetric gravitational field. And we will use everything that we developed till now, and we'll derive the equation. And remember, we solved this problem in lecture 2 classically. And we'll see what kind of modification we need to do to solve it relativistically. You see, it's not too much. So we started the Lagrangian that we spoke, we substitute the metric that we found. Now, the Lagrangian is independent on t. You see, under there's no t. T dot is a second variable. It's a independent variable. So there's no t inside. If there's no t inside, that means if you differentiate this by t dot, you'll get what that's called the t momentum. This is a conserved quantity. How you get the differentiation? You have 1 over the square root, and then you get the s, and this will be dt dot, and then differentiate this expression. T dot squared will give you twice. It cancels with the half c squared t dot, and you differentiate by t dot this, you'll get the remaining thing, which is c phi r dot. Those things don't have t dot, so that's the moment. Now we have here c in both places. We divide by c, and I want to calculate the square of this. Regular square difference, the square of the first term, twice the product, and the last term. To simplify this expression, what I'm doing, I'm using the four velocity. The four velocity is has always the same length, c squared, as you said, because it is the r, the s has the length 1, and the tau and the s are related by c, so u became the norm over c squared. Pay attention, that's only in case of massive object. What is nice in relativity, you can handle the same way also non-massive object, light, and you'll obtain also the same formulas for light. The only difference is exactly this line. In this line, we have for massive object, the four velocity is c squared. For non-massive object, massless object, the line interval is 0, as you have seen in lecture 4, I think. That means the objects with 0 mass, they must move with the speed of light. When they move with the speed of light, the interval became 0. So that's the only difference between massive and non-massive. Okay, what we do the following. We subtract from this formula this 1 times 1 minus phi r. Look what happens. The first term, if you multiply by 1 minus phi r, you get exactly the first term. It cancels. Multiply by 1 minus phi r, the second term, it became exactly this term. It cancels. We multiply this one by 1 minus phi r, we get 1 minus phi r squared. Open the parentheses, minus 1 plus phi r squared. Those cancels, and you are left only the phi r dot. And the c squared times this term is left, and this term is multiplied by 1 minus phi r is also left. So we got a new equation connecting us r dot and phi dot and r. Everything is known. That's equation number 1. This will be the basic equation to solve the problem. Let's try to understand what does this equation mean. This is the energy conservation. Constant means something is preserved on the trajectory, and C, it is nothing than the energy. If we multiply this equation by m over 2, then we can obtain mr dot square. R phi dot is exactly the transverse velocity. We get the transverse velocity square over 2, because we multiply over 2. The other term, which was phi and c square, if you substitute what the phi was, the definition, you'll get the potential. And the last term, what you'll get, the potential energy times the transverse velocity square over c square. This is constant. This is the new energy conservation equation. What is the whole difference? The first two terms are classical. That was in Newton's theory. You get an additional term, but this term breaks you the separation. You see here, this term depends on what? On the object, the velocity of the object. U depends on its position, independent on the velocity. And the new term that we obtained now depends on both position and the velocity. So we cannot have this separation, kinetic, potential energy, they became together. Now, if you look at the Lagrangian, there's independence also on phi. So we differentiate it by phi dot, and we obtain only one term, r squared phi dot, and this is conserved. That's the angular momentum conservation. So we have another equation connecting phi dot with r and j. Now we can rewrite the equation that we had. We had r dot square, we had 1 minus phi, and we had phi square plus with phi dot. And phi dot we can write a j over r square, and there was another r term that we can, so we got this expression. If you open the parentheses, then you get r dot square plus j square over r square minus c square phi r minus this term equals equal. Now the first two terms are exactly the velocity square, because that's the radial velocity, and j square over r square is from here. You see r phi dot is the transverse velocity, r phi dot square is exactly j square over r square. So this is really the full velocity. This is the potential energy, and this is the additional term, connecting the potential and the transverse direction. So let's compare the classical one. For the planetary motion, we had this equation. Let's look what we have here. We have r dot square, we had j square over r square, we have this term also, and it was here. We had only one term, this additional term, which really is multiplied by j square over r square. What I observed that's really fresh from yesterday, really this term we had. This is exactly the time dilation factor squared. The time dilation was square root 1 minus the r. So if j square over r square was the transverse velocity divided by d tau square, if you want to multiply by this factor, it became the rt, the transverse direction, by dt square. Very, very strange. The whole relativization, making the problem relativistic, we thought we moved to a new timing, the tau. But we moved to a new timing only in the radial direction, the direction of influence of the field. While in the transverse direction, we still have the regular velocity by time and not by tau. This already explains you why you get precession of the orbit. What was when you have elliptic motion, you have two times of motion, one going around, and the other one getting closer and getting further from the sun. That's an ellipse, how it's obtained. In classical case, both periods were the same. So therefore, you reach to the same maximal point when you made a whole circle. And therefore, the ellipse returns by itself. What happened in relativity, in the transverse direction, we didn't change the velocity, but we changed the velocity in the radial direction. So they will not be the same period. And therefore, we will reach the maximum, the perigee or the apogee will not be at the same angle. You'll go to pi and will not reach yet the maximum, and the maximum will be reached later. So this explains you the whole precession. people were always looking for some kind of force that is turning the ellipse. No, it is simply change in the velocities due to relativity in the two directions, in the direction of influence and the transfer direction. That's a new understanding what really relativity brought in. Now we want to solve. I repeated the equation that you'll remember what it is, and we're trying to solve it. We do the same thing as we have done for the classical solution. We move to the potential depending on the angle. We solve for this variable. Remember, for this variable, we had very simple equation, the harmonic oscillator. And that's what we know to solve. And here we'll get almost the same. So this is the same as to write phi was Rs over R. And therefore, we can write it Rs over R depending on phi. So we are solving for the trajectory only, not explaining how the timing will be on the trajectory. But if you know the trajectory, you have this equation for phi dot, the phi d tau, so you can tell you also the timing. So phi is depending on small phi. The derivative is defeated by the phi, the small phi, the var phi, which is differentiate such a thing. It's a Rs is constant. This is the power minus 1. This is the power minus 2. And the R d phi. Now, we repeated this one. The R d phi, we can write R dot over phi dot. Because the derivative with the R d phi is the same, the R d tau, by the phi d tau, chain rule. Using that phi dot is j over R square, we substitute this, and you got phi dot equals minus Rs over R, and the R square here cancels with this R square, and you get divided by j. Or R dot is equals minus j over Rs or times phi dot. So that thing we have to substitute here. And you see when you get the square, you get j square here, j square here. So what we'll do, we substitute this and divide by this expression square, which is Rs, or multiplied by Rs square over j square. What we will get? The first term, which was R dot, we multiplied, the minus disappeared. We multiplied by the inverse of it, so it became 1. So we get phi dot square. This term, j square over, we divide by Rs square and multiply by Rs square. J square over Rs square will be cancelled out. And Rs square over R square is phi square. So you have phi square minus phi cubed. And you have a term c square divided by those things, we called it mu. So that's the equation. For the potential, now we rewrite it in the following form. Phi dot square equals this expression. I organized it by the powers. I took it on the other side. And now look, this expression is very close to the one that we got for the classical motion. The only difference is this additional term phi in power 3. The rest was exactly the same. Why it is close? Phi is Rs over R is in general very small number. For Mercury, it is 10 in power of order 10 in power minus 7. It's a unit-free number. It's absolute values. It's a small number. So phi squared is even smaller, and phi cubed is much smaller. So really, this is an approximation to the classical orbit. In the classical orbit, we define the orbit by checking where this phi prime vanishes. What means phi prime vanishes? phi prime, the potential vanishes at what angle? Where the you get the closest to the sun or the furthest to the sun. When you are closest to the sun, you call it perigee of the orbit. When you are the farthest from the sun, is the apogee. So really, this polynomial has two roots. One is related to the apogee, the other one to the perigee. So you have phi minus the perigee and phi minus the apogee. I put the minus sign because for the classical one, you had this minus here, and you had the minus. So the classical one was this one. The new ingredient will be another third root. Because a third order equation, you have two real roots. You have the third one is also real, and it is denoted by phi e for Einstein. That's the Einstein's root. Since I put out the minus outside, I have to change the order and write phi minus phi. And as you'll see in a minute, it is more reasonable to write it, because if you can find what is this phi e, how you use, if you have three roots, that the sum of them is the negative of coefficient of phi squared, the quadratic term. That's from linear algebra. And so you'll have phi p, phi a, and phi e add up to 1. That means phi e is 1 minus phi p minus phi a, which are both two small numbers. That means phi e is close to 1. So therefore, I write it in this way. So this expression, when you approach the classical one, gets 1. Now, what you can find out how from this term, this 2 mu, that phi p plus phi a is approximated. Since they are small, to get this coefficient, you have to take the product of all of them. And when you take the product of all of them, you get order phi square and the order phi. And you can ignore phi square, so you get 2 mu. So 2 mu is like the average energy on the trajectory, which is the energy of the at the perigee and the apogee. From here you got this additional root is 1 minus twice mu from here. So we know what it is value and how it's related to mu. Okay, now we have to solve this equation. And we do exactly what we have done in the classical with a slight modification. Look, the classical solution was that we got mu, the same mu that we got, 1 plus epsilon cos alpha, cos phi. We had phi of phi minus phi naught. That's what we got for the classical solution. Now we use the following trick. Here we draw the picture in green. I draw the classical solution, an ellipse. It goes from the value for the perigee to the apogee. The perigee and apogee are now also the same, because also our solution has two maximal points, which are the perigee and the apogee. So if you draw the circle for the perigee and the circle for the apogee, our ellipse always has to go between the two circles. So what we can do, we can, for each point on our trajectory, which is in red, find the nearest point on the classical circle and call it this alpha corresponding to the angle phi. That's what is alpha phi. Alpha phi is you have an angle phi minus phi naught here. You have this angle, and you look where at the same radii was the classical solution, at what angle? Alpha. So that is the form of our solution. We can look for such a solution, and the reason is why we do, because we have seen that our solution is close to this, and we'll be able to solve it. That's the main proof that it works. We got something solved. So we have to substitute in our equation. In the equation, we had this expression. We substitute, and we get an expression. We have a phi dot. We can substitute, differentiate it, and we get this one. We get the derivative of this one, mu epsilon, cosine will give you sine, alpha phi, and alpha prime of phi. Now, those two things turn out to be the same, and that should be the same because those two terms came from the classical solution. In the classical solution, alpha was the identity name, which has derivative 1. So, and we have to check this additional term. This additional term, the Einstein's term, Fe minus phi, is Fe was 1 minus 2 mu, and we subtract a mu from phi, and we have, oh, I'm missing here another mu with epsilon. Missing a mu. Okay, I'll add this mu. But, okay, so this is the expression. Now let's substitute in the equation. So what we'll get, phi dot square equal, that was the equation, number 2. So phi dot square, we have those terms which you cancel out. You get alpha dot square equals this expression. So alpha dot is the square root of this expression. So you got an equation, first order differential equation for alpha dot. We will solve it. We solve it, we will not solve as a differential equation. We will solve it by taking the integral of both sides. Now, what we do, we can write the phi d alpha is 1 of the square root. So I write the phi d alpha as this. And phi of alpha is phi naught plus the integral of from 0 to alpha of the phi d alpha, and we put in the variable alpha tilde, which is this expression. Okay, now what is the precession? Precession tells you when we will reach, alpha will reach 2 pi. So we have to check what will happen when we went from 0 value alpha till we go a full circle. So we'll see what happened with the whole thing, and we'll see where it reached. It reached to a different point, and we'll get this point. I will get it, this phi of 2 pi minus phi of 0, the value of 0. And we have to subtract the 2 pi, which would be, if it would reach the same point, it would get no precession. But we can calculate what it is. How you calculate it? So we have to calculate this integral. The integral from 0 till 2 pi, this term 1 gives you 2 pi, which will cancel with 2 pi. Phi 0 will cancel with this phi 0. And we'll get the next term will be 3 mu. Now the power 1 minus half turns out 3 mu over 2 times 2 pi, which is 3 pi mu. That's a nice formula for the precession per one circle, one ray. Okay, let's look what are the numbers. If you consider the RA for the Mercury and the perigee distance, and RS of the sun is about 3 kilometers. You calculate them, you see when you divide, you get order 10 in power minus 7. 3 and this is order 10. And you get the mu. Oh, you don't see it. Okay, you get the mu. You see it now. Delta phi gives you 5 times 10 in the power minus 7 radians per revolution. Now, to get exactly the 43 arc seconds per 100 years, you have to know the period of the Mercury, divide it in 10 years, how many periods, multiply by the number of periods, and turn radians into arc seconds, and you get exactly 43 arc seconds per 100 years. That was the main result that proved for Einstein that his general theory of relativity is valid. As he wrote in his notes that when he obtained this result, he had 3 days problems. His heart was so beating so strong, he was not sure that he would survive it. And he thought, the first time I have seen that I obtained something that the nature spoke to me. I able to obtain a result that for a long period people were not able to obtain it. And that was the big proof of his theory. So with this, we solved all the steps how to get the right formula for precession of Mercury for any orbit. And we see from where it comes. It comes this additional term that we obtain in the differential equation because we had the different timings for the velocities. We obtained, this was resulting in an additional term for the potential of order 3, which gives you an additional root, which is 1 minus 2 mu, and this eventually gives you the 3 mu times pi. Motion of light in a stationary phase with symmetric gravitational field. And at the beginning, we do almost the same that we have done earlier. Once more, we look the Lagrangians independent on t. That's the same thing as we had earlier. We got the same potential, but pt, and pt over c squared is the same formula. But the whole difference is here, that the for velocity is now not c squared, it has length 0. And when you do the same thing, subtracting, we got a different differential equation, a simpler one. Only 2 terms. That's equation 1 prime. Then we use the same thing as we had earlier, the Lagrangian independent on the angular momentum. So you have the same angular momentum conservation also for light. That's very interesting. And we get the light trajectory, we're substituting this inside here. The R, we can go into the R d phi. The R d tau, we divide by the phi d tau, you'll get the R d phi, and you'll get this equation. That's equation number 3 for the light trajectory. R is a function of phi. And now we see how we got the solution. So the picture looks the following. We have the sun, and light is coming from sun star, and we are receiving it on the Earth. When you can see the deflection of light, to see deflection of light, you have to have an eclipse of the sun, as we had a few days ago, when the moon is covering the sun, so we don't see the light coming from the sun, but you can see the stars near the sun. So if the sun is bending the light, you see them at a different angles with respect to the other stars which are far away than when they are far from the sun. This is a proof of deflection of light. And this was considered by Eddington in I think in the First World War. I don't remember. It was eventually the other proof of GR theory. Now I repeated the formula that we got on the previous page. That is the formula for the motion of light as R of phi. Here we don't have to go to phi or phi for the potential. We can solve it directly for R of phi. So we start here. In the previous case, we had 2 initial conditions. We had the perigee and the apogee, because the trajectory had 2 extremal points where the velocity, the R dt gets 0, 2 extremal. But for this problem, this motion is not by an ellipse. It is a hyperbola, so it has only 1 extremal point, the closest approach to the sun, which is denoted by R0. Here, this is the distance from the sun to the trajectory of the light. Now, from equation 3, at this point, the derivative of the RdP is 0 because it's an extremal point, the closest point. So we have only the two terms, and we can find the connection between J and E. Simply take the coefficient near J square on the other side and put R0. Okay, so substitute this in this equation for J, and you get all the places E, and you cancel out E, and you obtain the following equation. Now you eliminated both J and E. That means it's fully depending only on one parameter, R0, the closest approach. So you have an equation for light which depends only on one parameter, how close it gets to the sun. How you solve it? The same idea as we used in the previous problem. Use the classical trajectory and see how you moved from the classical to this. The classical trajectory is a straight line going to this R to the point P. Now what you do, if you want to find R of phi, use the same R circle as we have done previous time and see where it crosses the approximation, the classical trajectory. Call it R tilde, which is the same as R. And for R tilde, you know the angle, because alpha, sine alpha is R naught over R tilde, so you know R tilde of alpha is R naught over sine alpha. And since it is the same as R of phi, so we know R of phi in terms of alpha of phi. Now we have to calculate this. I want to substitute everything in the formula above. So I have to calculate the RdP. I'll calculate the RdP in this formula. The derivative of the denominator square and minus R naught times the derivative of the denominator cosine times alpha prime. Okay, so we have now we have sine square alpha is R over R naught. Substitute from here, R naught over R, and you get R square, and you'll get R naught square, which cancel out with this R naught, and you get R naught, this expression. You see, when you substitute here, the R naught and this R naught and the R square with this R square will cancel out, and the equation becomes very simple equation. You get this cosine square, the alpha d phi square equals this one from here. What is this expression? R naught, we multiply by Rs. R naught over R square is sine square. So we have this sine square here. And this Rs over R, I can write it Rs over R naught over Rs, R, which is once more sine. So you'll get here sine cubed. So you'll get 1 minus sine square. And we have Rs over R naught from here. And this one gives sine cubed alpha. Nice expression. Now divide by cosine square. Divide by cosine square. This is cosine square. It gives you 1. And here you get the 1 from here by cosine square. And this one gives 1 minus sine cubed, 1 minus sine square. Okay, you remember from algebra, 1 minus sine square is 1 minus sine, 1 plus sine. 1 minus sine cube is 1 minus sine times 1 plus sine square. So 1 minus sine cancels out. You're left with 1 plus sine. The first one you leave it here, 1 plus sine. The second and the third one, sine plus sine square, cancels with the denominator. And you're left with sine. So you get a very nice expression for the alpha dp. Okay, now really we want to find dphi d alpha, so it's 1 of the square root of this, and you're expanding it. Rs of R naught is a small number. You saw for the sun, Rs is 3 kilometers. The size of the sun is thousands of 10,000 of kilometers. So it's really, even the outside the sun is already a small number. And for sure you cannot get exactly on the surface of the sun close. So that's a small number. So expand this expression, and the first term will be minus half, will be take it to plus half of the same expression. And now you integrate it. Okay, since you don't see it, you'll have to go out for the PowerPoint presentation. Okay. So we'll get delta phi is the integral. Now what I want to get? I get this expression. Now I want to get, we can assume that the Earth and the star are almost at infinity, because they are very far with respect to the closest approach to the sun. So we'll integrate it when the star we have started, it was corresponding to the angle alpha 0. At infinity for the straight line is the 0. When it reaches this point, it is alpha pi of the whole expression. And you have to subtract pi to see the difference from the straight line. So when you integrate this one, the first term gives you pi minus pi gives you 0. So you get the same expression, Rs over 2 R naught. And these two integrals. Integral of sine is cosine from 0 till pi gives you 2. The integral 1 over 1 plus sine alpha is also a table integral. And from 0 to pi, it gives you 2. So the two expressions give you 4. Cancel with this, and you get 2 Rs of R naught. Substitute the value for Rs, which was 2 gm over c squared, and that's exactly the angle of deflection predicted by Einstein. So really, we also obtained exact formula for the deflection of light as predicted by GR, and that was the second prediction. So really, we resolved all the shortcomings that we mentioned by GR. There is another test of GR was called Shapiro time delay, but it is basically the same, checking on this trajectory, on the light trajectory, the timing, the difference in the time by using the straight line and this time. And it uses the same formulas that we developed for the motion of light and the same approximation. So I didn't repeat it. It's a lot of technical issues on it. So really we finished about how you can look on relativity of gravitation. We have seen the difference between the previous things is here we get the dependence on the forward velocity was quadratic, and we have seen that it gives you something for the transverse direction that it's not depending on the tau, it's depending on the time t. Maybe the next time I'll explain you a little bit from the time dilation formula. It has new predictions and how we plan to compare it with the test of the satellite. And maybe it will be needed for the next accuracy of the clocks on the satellite. That's about, next time I want to add a few more points, but mainly to summarize, to see how this can be put in a picture, to explain a little bit some ideas how to go from here to quantum, and to have some kind discussion at the end, what we will do to continue this research. Okay.
Thank you. Thank you, and thank you, and bye-bye.